They said it was too heavy to even leave the yard. So how did this 290-ton monster outpull 4 diesel locomotives combined and make the railroad more money than anything else on their roster? Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old trains like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel, and let's keep these old trains' legacies alive. By 1950, American railroads were racing toward diesel, and steam's defenders were running out of time. The Chesapeake and Ohio, Pennsylvania Railroad, and Union Pacific had all placed their bets on the future, ordering fleets of diesel electrics that promised lower costs and easier maintenance. But in Roanoke, Virginia, a different conversation was taking place. Norfolk and Western's engineering department had spent 2 years drafting plans for a locomotive that flew in the face of conventional wisdom. The design called for a compound articulated engine with a 2882 wheel arrangement, massive cylinders, and a boiler pressure that would push the limits of metallurgy. On paper, the machine looked like a monster. The projected weight came in at over 580,000 pounds for the engine alone, nearly 290 tons of steel, brass, and cast iron before a single piece of coal touched the firebox. When the initial specifications reached the desk of Robert Hall, Norfolk and Western's chief mechanical officer, the response from the industry was swift and brutal. Trade journals questioned the sanity of building such a behemoth. Engineers from competing railroads sent letters warning that the axle loads would destroy track infrastructure. One consulting firm calculated that the locomotive would require complete track rebuilding on any line it operated, with costs running into the millions. The American Railway Engineering Association published guidelines stating that axle loads above 70,000 pounds posed unacceptable risks to rail integrity. Norfolk and Western's design pushed several axles past 72,000 pounds. Track superintendents across the system voiced concerns about bridge stress, rail fatigue, and the possibility of catastrophic derailments on curves. Insurance underwriters threatened to raise premiums if the locomotive ever left the shop. Financial analysts joined the chorus of skepticism. The cost to build each unit was estimated at over $250,000, nearly double the price of a modern diesel-electric with comparable horsepower. Maintenance projections suggested the heavy components would wear out faster, requiring constant attention from an already stretched workforce. The math seemed clear. Norfolk and Western was about to waste a fortune on an outdated technology that would break the railroad's back, both literally and financially. But Robert Hall and his team in Roanoke had run their own calculations. They knew something the critics didn't. Norfolk and Western's main line through the Appalachian coalfields was unlike any other railroad in America. The grades were steep, the curves were tight, and the loads were immense. Diesel units struggled in multiple locomotive configurations, and the existing steam fleet was reaching the end of its operational life. The railroad needed power, raw and uncompromising, and Hall believed that weight, properly distributed, could be the answer rather than the problem. Construction began in Norfolk and Western's Roanoke shops in late 1951. The project demanded precision that pushed the facility's capabilities to their limits. Master craftsmen worked alongside engineers, translating blueprints into a machine that would either validate years of theory or become the railroad's most expensive mistake. The frame alone required special casting techniques. Traditional methods couldn't produce the structural integrity needed to support the massive boiler and articulated design. Norfolk and Western's foundry developed a new alloy blend, combining manganese steel with trace elements that increased tensile strength without adding brittleness. Each frame section was poured in a single continuous process to avoid weak joints, then stress-tested under loads that simulated years of mountain railroading. The boiler presented its own challenges. To generate the tractive effort Hall's team had promised, the Y6B needed steam pressure of 300 pounds per square inch, higher than any previous Norfolk and Western design. The boiler's firebox measured over 108 square feet, large enough to generate massive volumes of steam, but requiring careful engineering to prevent hot spots that could cause metal failure. Welders worked in rotating shifts, inspecting every seam with magnetic particle testing, a relatively new quality control method borrowed from aircraft manufacturing. The compound cylinder arrangement was perhaps the most controversial element of the design. High-pressure steam would enter smaller cylinders on the rear engine, then exhaust into larger low-pressure cylinders on the front engine. This system promised to extract maximum energy from every pound of steam, but it also meant coordinating the timing of 4 massive pistons, each weighing over 800 pounds, and moving at speeds that could shatter cast iron if the balance was even slightly off. Precision machining of the driving wheels required tolerances measured in thousandths of an inch. Each wheel measured 57 inches in diameter and was balanced to within 2 pounds across its entire circumference. The axles, forged from nickel steel, underwent magnetic inspection and ultrasonic testing to detect any internal flaws that could lead to failure under the enormous forces they would endure. By the spring of 1952, the first Y6B stood complete in the erecting bay. Workers gathered around the locomotive, their faces reflecting a mixture of pride and uncertainty. The machine dwarfed everything else in the shop. Its lines were brutal and functional, with none of the streamlined aesthetics that marked passenger engines of the era. This was a locomotive built for a single purpose: to haul coal trains up mountain grades that had humbled every other engine on the system. The moment of truth approached. In a few days, the Y6B would roll out of the shop for its first test run, and the world would discover whether Norfolk and Western had built a masterpiece or a very expensive piece of scrap metal. The date was April 14, 1952, and the sky above Roanoke hung heavy with gray clouds. The Y6B rolled out of the shop under its own power for the first time, steam hissing from every joint as the crew brought pressure up to operating levels. A small crowd of railroad officials, engineers, and shop workers gathered trackside, their expressions ranging from hopeful to deeply skeptical. The test route had been carefully selected, a 47-mile stretch of main line between Roanoke and Bluefield, West Virginia, including some of the steepest sustained grades on the Norfolk and Western system. The locomotive would pull a train of loaded hoppers weighing 6,200 tons, a load that typically required 2 or even 3 older engines working together. Chief Engineer William Collins climbed into the cab alongside the regular crew. His job was to monitor every gauge, record every measurement, and document whether the Y6B could deliver on its promises or if the critics had been right all along. The locomotive's weight distribution was his primary concern. If the axle loads proved too much for the track, the entire project would end before it truly began. At 6:15 a.m., the engineer notched the throttle forward. The Y6B's exhaust cracked across the rail yard like artillery fire. The massive drivers bit into the rails, and slowly, deliberately, the train began to move. Within minutes, they were clear of the yard limits and accelerating toward the first grade. The climb began at milepost 12, where the track pitched upward at a sustained 1.2% grade. This was where older engines typically slowed to a crawl, their fireboxes glowing white-hot as firemen shoveled coal as fast as humanly possible. Collins watched the speedometer. The Y6B held 18 miles per hour up the grade without strain. The compound cylinders worked in perfect harmony, exhausting steam from the rear engine into the front with a rhythmic precision that sent shivers through the frame. At milepost 28, they hit the steepest section, a brutal 2.1% climb that curved through a rock cut. This was the moment that would define everything. Collins' pencil hovered over his notebook as he watched the steam pressure gauge. The needle held steady at 285 pounds. Speed dropped to 14 miles per hour, but the locomotive never faltered. The drawbar pull meter showed forces exceeding 166,000 pounds, numbers that made Collins blink and check the gauge twice to confirm he was reading it correctly. By the time they crested the summit at Bluefield, the Y6B had climbed over 2,000 feet in elevation, while hauling a load that would have required a diesel consist of 4 units. The critics had predicted rail damage, wheel slippage, and mechanical failure. Instead, the locomotive had performed flawlessly. Back in Roanoke, the accounting department faced a puzzle that defied conventional railroad economics. The Y6B's performance numbers were undeniable, but translating raw power into profit required a different kind of analysis. Transportation costs in the coal industry operated on razor-thin margins. Every additional locomotive in a consist meant another crew, more fuel, and higher maintenance expenses. The Y6B's ability to haul loads single-handedly that previously required 2 or 3 engines represented a fundamental shift in operational economics, but only if the maintenance burden didn't erase those gains. Norfolk and Western's comptroller, James Marsh, ran the numbers with meticulous attention. His initial calculation showed that despite the Y6B's higher purchase price, the locomotive could move a ton of coal 1 mile for .43 cents, compared to .67 cents for a typical diesel consist on the same routes. The difference seemed small until multiplied across millions of tons of coal hauled annually. On paper, each Y6B could save the railroad over $180,000 per year in direct operating costs. The weight that critics had called impractical proved to be an asset in unexpected ways. The Y6B's massive drivers and high adhesion weight meant it could start heavy trains on grades where lighter locomotives spun their wheels uselessly. This eliminated the need for helper engines on many routes, cutting costs further and reducing congestion on single-track mountain lines. Fuel efficiency told another surprising story. The compound cylinder design extracted more work from each pound of steam, and the large firebox could burn lower-grade coal that cost significantly less than the premium grades required by smaller, higher-pressure boilers. Fuel costs per ton-mile came in 22% below the older articulated engines still in service. Maintenance patterns emerged over the first 6 months of operation that challenged industry assumptions. Yes, the Y6B's components were heavy and required specialized handling equipment, but the robust construction and conservative stress levels meant components lasted longer between overhauls. Driving wheels that were expected to need turning every 80,000 miles were still in tolerance at 120,000 miles. Boiler tubes built with extra thickness to handle the high pressure showed minimal corrosion after a full year of hard service. The most dramatic savings came from crew efficiency. A single Y6B with a 3-man crew could replace multiple locomotive consists that required 9 or more men. In an era when labor contracts were driving costs upward across the industry, this advantage alone justified the locomotive's existence. By late 1952, Norfolk and Western's board of directors received a report that reversed their initial skepticism. The Y6B wasn't just viable, it was the most cost-effective locomotive the railroad had ever operated. The decision to order additional units came swiftly. Critics who had predicted financial disaster now watched as Norfolk and Western's coal division posted record profits while running fewer locomotives than any comparable operation in the country. Winter arrived early in the Appalachians that year, and with it came the conditions that separated legendary locomotives from ordinary machines. On December 3, 1952, a blizzard swept through West Virginia, dropping temperatures to single digits and coating the rails with a treacherous mix of ice and snow. Norfolk and Western's dispatcher faced a critical problem. 32 loaded coal hoppers sat in the yard at Bluefield, bound for the steel mills in Ohio. The train weighed 7,100 tons, and the route ahead included grades that had defeated multiple diesels in good weather. In these conditions, most operations would have shut down until the storm passed. Instead, the dispatcher called for Y6B number 2171. Engineer Tom Bradford had been running steam locomotives for 23 years, and he approached the assignment with the caution of a man who had seen weather destroy trains and careers. His fireman, Richard Hayes, built the fire carefully, bringing the boiler pressure up slowly while watching for any signs of uneven heating that could crack cold metal. They departed Bluefield at 4:30 a.m., pushing into darkness and horizontal snow. The first test came within 2 miles, where the grade steepened to 1.8% through a curve. Bradford eased the throttle open, listening to the exhaust rhythm for any hint of wheel slip. The Y6B's massive weight pressed down on the rails with over 380,000 pounds on the drivers alone. Instead of spinning uselessly on the ice like lighter engines, those wheels found purchase. The compound cylinders delivered their power in a smooth, sustained surge that kept constant tension on the drawbar. Modern diesels delivered their power in sharp pulses that could break traction on slippery rails. The Y6B's steam delivery was continuous, its momentum building gradually but inexorably. Bradford held the train at 11 miles per hour up the grade, a pace that would have been impossible for any other single locomotive in those conditions. At milepost 34, they encountered drifting snow deep enough to bury the rails. The Y-6B punched through like an icebreaker, its massive pilot and cylinder casings bulldozing snow aside while the drivers continued their relentless rotation. Hayes kept the firebox roaring, shoveling coal with practiced efficiency while monitoring the water level in the glass. Steam pressure held at 295 pounds just below the safety valve setting. 6 hours after departure, they rolled into the receiving yard in Portsmouth, Ohio. Other trains had turned back or were stuck, waiting for track crews to clear drifts. The Y-6B had conquered mountains and weather that had shut down modern diesels. Word spread quickly through the railroad community. Trade journals that had mocked the locomotive's excessive weight now published articles praising its stability and traction. The machine critics called too heavy had used that very weight to achieve what lighter, more practical locomotives could not. By 1954, diesel manufacturers were watching Norfolk and Western's Y-6B fleet with growing concern. The locomotives had demolished the narrative that steam was obsolete, and they had done it with embarrassing thoroughness. Electromotive Division, the dominant force in diesel manufacturing, decided to settle the question definitively. They proposed a head-to-head test. Their latest GP9 road switchers, configured in a 4-unit consist totaling 7,200 horsepower, against a single Y-6B rated at 5,600 horsepower. The route would be Norfolk and Western's toughest: Williamson, West Virginia to Portsmouth, Ohio, 128 miles of mountain railroading with sustained grades and tight curves. Both trains would haul identical 6,800-ton coal drags. Norfolk and Western agreed, seeing an opportunity to validate their investment. The test would be conducted under the observation of Railway Age magazine, ensuring credible, independent documentation of the results. The diesel consist departed first on a clear morning in May. 4 GP9s, gleaming in fresh paint, accelerated smoothly out of the yard with their characteristic turbocharged whine. The lead engineer managed the multiple unit controls with practiced ease, coordinating the output of all 4 prime movers. On level track, the diesels ran flawlessly, settling into a steady 40 miles per hour cruise. The first major grade changed everything, as the track pitched upward at 1.6%. The lead engineer advanced the throttle to run 8 position, calling for maximum power from all 4 units. The diesels responded, but their speed dropped to 17 miles per hour. The loads on the traction motors climbed toward their thermal limits, and the engineer had to ease back slightly to prevent overheating. They crested the grade at 14 miles per hour, having consumed 620 gallons of diesel fuel in the process. 2 hours later, the Y-6B made the same run. Engineer Bradford kept the compound cylinders working in their optimal range, letting the locomotive's momentum and massive adhesion weight do the work gravity opposed. The Y-6B climbed the grade at 16 miles per hour without strain, its steady exhaust beat never varying. At the summit, the firemen reported they had burned 2.8 tons of coal, which cost Norfolk and Western $11.20 at current prices, compared to over $124 for the diesel fuel consumed by the 4-unit consist. The final numbers told an uncomfortable story for the diesel manufacturers. The Y-6B completed the run in 5 hours and 42 minutes, burning $48 worth of coal. The diesel consist finished in 5 hours and 51 minutes, consuming $487 worth of fuel. When maintenance costs and crew requirements were factored in, the economic advantage of the single-steam locomotive became overwhelming. Railway Age's article, published in June 1954, carried the headline, "Steam's Last Stand Proves Stronger Than Expected." The Y-6B fleet would serve Norfolk and Western until 1960, when the railroad finally completed its transition to diesel, driven not by economics, but by the declining availability of skilled steam crews and the closing of coal-fired fueling facilities across the industry. Even in retirement, the Y-6Bs had proven their point with devastating clarity. Preservation was never a question. Norfolk and Western retained several Y-6Bs in operational condition well into the 1960s, using them for special movements and as a hedge against diesel parts shortages. Today, multiple examples survive in museums, still capable of operation, still inspiring awe in observers who see them for the first time. The engineering lessons from the Y-6B program rippled far beyond steam locomotives. The compound cylinder principles influenced industrial compressor design. The stress analysis techniques developed to verify the frame's integrity under extreme loads became standard practice in heavy equipment manufacturing. The metallurgical advances in boiler construction found applications in chemical processing and power generation. Modern railroad engineers studying the Y6B are struck by how closely its designers came to extracting the theoretical maximum performance from steam technology. Computer modeling, conducted decades after the locomotives were scrapped, confirmed that the Y6B operated within a few percentage points of the thermodynamic ideal for its configuration. The critics who called it too heavy had failed to understand that in the specific context of Appalachian coal railroading, weight was not a liability but a carefully calculated advantage. The Y6B also served as a cautionary tale for the diesel industry. The assumption that newer technology always supersedes older technology proved dangerously simplistic. Context mattered. Operating environment mattered. The specific demands of the work mattered more than abstract comparisons of horsepower and modernity. In recent years, as railroads explore battery electric and hydrogen fuel cell locomotives, engineers have returned to studying the Y6B's story. They find parallels in their own struggles. Critics who dismiss new technologies as impractical, financial analysts who focus on purchase price rather than life cycle costs, and the challenge of proving that unconventional solutions can outperform established alternatives. Norfolk and Western's willingness to ignore conventional wisdom and build a locomotive that critics called absurd created a machine that dominated its era and outlasted the predictions of its demise. The Y6B stood as proof that sometimes the heaviest solution is the right solution and that the weight of evidence matters more than the opinions of critics. The locomotive they said would destroy the rails became the machine that carried Norfolk and Western to unprecedented profitability. The heavy weight that accountants called financial suicide generated returns that justified every pound of steel and every dollar invested.